Hello and welcome back to the course on Introduction to Solid-State Physics. This video is a repetition to my last lecture because the audio quality was very poor. So now with this better audio quality we can have this lecture. So in our last lecture we have discussed about the Phonon dispersion relation for a one-dimensional monoatomic chain, and this is the required dispersion curve. And this for monoatomic chain, this translational as well as mirror symmetry is written because from the associated relation we can see that omega minus q is equal to omega of q. In today's class we will be slightly altering the problem. That means we are going to have a linear monoatomic chain. Earlier we had a monoatomic chain. Now we are going to change it to a diatomic system. That means we are having two different types of atom. One is having a heavier mass and the other type of atom is having a lighter mass. And in this case the periodicity of the lattice is no more a, rather it is 2a, because every 2a distance we can see the repetition of the same unit, and rest of the terms remain the same. Un corresponds to the displacement from the equilibrium position for the nth atom, and here you can see a series of atoms, capital M, small m, in this manner with a periodicity of 2a. So what we are doing here is that for the even numbered atoms we are assigning the heavier mass m, and for the odd number atoms we are assigning the lighter mass smaller m. So in this case, since it extends to infinity, here the number of atoms is very large, tends to infinity, and under this criteria we can assume that all the capital M atoms are having the identical surrounding, whereas the small m atoms are having the identical surroundings, and the spring constant for both these systems it remains the same, it is the small k. And we are discussing the problem under the elastic limit, for which the Hooke's law is obeyed. That means the force, elastic force, is proportional to the displacement from the mean position. Now with this schematic, let us try to solve the problem. So as before in our last class we had written down the equation of motion, but in this case since there are two different types of mass, so we have to write two different equations of motion, one for the capital mass, capital M mass, and other one is for the smaller m mass. So let us do that. And first as I mentioned here, the even numbered atoms are designated as heavier mass. So we can take the atoms which are designated with the even index, that is 2n, n is an integer, so 2n will always be an even number, and the associated atom will be having the heavier mass capital M, and this capital mass, capital M mass, is having two neighbors, and both the neighbors are having the smaller mass m. So for the 2nth atom the associated neighbors are 2n plus 1 and 2n minus 1, but this 2n plus 1th atom and the 2n minus 1th atom are having the mass small m, whereas the 2nth atom is having the mass capital M. So in the similar manner as we had done in our last lecture for the monoatomic chain, the same thing can be applied here. Here the first term correspond to the 2n plus 1th atom, and the last term correspond to the 2n minus 1th atom, but only the difference is that their masses are having different masses. So capital M times the acceleration, that is d square u2n by dt square, is equal to k into u2n plus 1 minus 2 u2n plus u2n minus 1. As I mentioned here, once again I would like to repeat, u2n plus 1 is the displacement from the equilibrium position for the smaller mass m. Similarly 2n minus 1th atom is also the displacement for the smaller mass m, whereas this 2nth atom is the displacement from the equilibrium position or the mean position for the capital mass M. Similarly, we can write the corresponding equation of motion for the odd indexed atoms. This 2n minus 1 can be taken to be an odd number. For any integer n, 2n minus 1 will be an odd number, and the mass associated with that will be small m. Now we can write the corresponding equation of motion for this. That will be small m times d square u2n minus 1 by dt square. For the 2n minus 1th atom, that is small m, we are having the associated neighbors, that is capital M, and this capital M are having this displacement u2n and u2n minus 2. So u2n minus 2 is the displacement from the mean position for the capital mass M, which is situated to the right of this 2n minus 1th atom, and this is for the 2nth atom, which is also having the heavier mass M, whereas u2n minus 1 is for the smaller mass M, which is situated at 2n minus 1th location. And in both the cases we are going to have the same spring constant K. Now we are having these two equations of motion. Now you can assume the progressive wave or the traveling wave solution for these two atoms. These are the corresponding traveling wave solutions, and here once again you can recall that the equilibrium position can be written in this manner, that is x and 0 is equal to n times a. Similarly, for the 2nth atom, x2 and 0 will be 2na. In this case, this 2n and a has been written for this 2nth atom. So if you recall, this term contains q into x. I qx minus omega t is the phase factor. So x is the mean position for the 2nth atom, and in this case it is 2na. And also we should see that the amplitude of vibration is a, whereas for the lighter atom that is placed at 2 minus 1th position is having a different amplitude. Both of them cannot have the same amplitude because they are having the different masses. Similarly, here x 2n minus 1 0 will be equal to 2n minus 1 times a. So here you can see the 2n minus 1 term here. Now we are having these two solutions to the equations of motion we obtained for the capital mass, capital M and small m. Now we can put the solution back into the equations of motion, and we can get to one set of homogeneous equations with the unknown coefficients a and b. So the form of the equation almost remain the same, but we should be careful in looking at the coefficient. So here you can see for the term 2k minus omega square m, the coefficient from the first equation is coming to be a, whereas for the second equation it coming out to be b, because of the different amplitude of vibrations for the capital M and small m. Because the masses are different, that's why the amplitudes are different. As a result, we are able to see the different coefficients for the same kind of terms here. Now these unknown coefficients a and b can be obtained through the solution of this set of homogeneous equations. Now the non-trivial solution will exist if the corresponding determinant of this term are 0. The trivial solution is that a and b are 0, but we are not interested in that. We are interested in the non-trivial solution which exists if and only if this determinant of this 4 term is 0. This is the associated determinant which I was talking about. So the determinant of 2k minus omega square capital M minus 2k cos qa minus 2k cos qa. Here you have to see that 2k minus omega square small m is equal to 0. Now we can find out the determinant of this particular thing, and we can evaluate it, and we can obtain a quadratic equation in omega square. So that I am not going to completely derive it here. So after getting the quadratic equation in omega square, you will get an equation of this form: ax square plus bx plus c is equal to 0, where x is equal to omega square. So this is a quadratic equation in omega square, and this coefficients a, b, c, we can get it, and we know the solution for this. X will be equal to minus b plus minus root over of b square minus 4ac whole divided by 2a. So the solutions can be written in this form, that is omega square is equal to k into 1 by capital M plus 1 by small m plus minus k into 1 by capital M plus 1 by small m whole square minus 4 sine square qa by small m into capital M, and the square root of this will give you the Phonon dispersion relation. Basically, this is a relation between the frequency, angular frequency, and the wave vector. But one interesting feature, you can see it here, is that there is a plus minus sign here. That means omega will have two different values depending on the plus and minus sign. So one value will be higher and the other value will be lower. If we plot omega is a function of q in the first Brillouin zone, which extends from minus pi by 2a to plus pi by 2a, because in this case the periodicity is 2a, it is no more a, this periodicity is 2a. So the first Brillouin zone is from minus pi by 2a to plus pi by 2a, and this is what is the associated Phonon dispersion relation. Here we can see there are two branches. The higher frequency branch is called as the optical branch, and the lower frequency branch is called as the acoustic branch. And why the nomenclature is like this? Because as q tends to 0 for the acoustic branch, we can see it is omega versus q relation is almost linear. If it is linear, there is no dispersion and it is equivalent to the sound waves. Sound means acoustic, that's why this branch is also called as the acoustic branch. And for the higher frequency branch, we can see as q tends to 0, the frequency lies near to the higher region or to the optical region. That's why the name is optical branch. Now let us focus on this q equal to 0. When we put q equal to 0 in the dispersion relation, we can get the frequency to be root over of 2k 1 by capital M plus 1 by small m. And at the boundaries of this first Brillouin zone, that is at pi by 2a or at minus pi by 2a, these branches are separated through certain frequency interval, and that the higher frequency at the boundary is root over of 2k by small m, which is the mass of the lighter atom, and for the acoustic branch at the boundary it is root over of 2k by capital M, which is the mass of the heavier atom. So we should always remember that capital M is having heavier mass, is heavier than small m. And here we can see there is certain region at which no frequencies are allowed. So this is just like the forbidden region in a band picture, and because of the existence of this kind of forbidden region, this diatomic linear chain can be used as a band pass filter, because the frequencies in this band is not allowed. So this can be used as a band pass mechanical filter. On the other hand, if you recall, for the monoatomic chain, there was a certain cutoff limit, that is omega max, above which no frequencies were allowed. That's why for a monoatomic chain, it can be used as a low pass mechanical filter, whereas a diatomic chain can be used as a band pass mechanical filter. So this is all about the phonon dispersion relation, that is the relation between the angular frequency and the wave vector for the elastic waves inside the solid at a particular temperature. In the next module, we will be discussing about the electronic properties of the solid. Till now we have some idea about the electrical properties of the metals, some thermal properties, and the crystal structure of the solids. In the next class, we will be trying to find out the difference between the metals, semiconductors, and insulators, and to know that we must have an idea about the energy band diagram. So the details about this we'll be discussing in the next module, which is mostly associated with the electronic structure of the solids. Thank you.